Take a look at this city intersection. The real world is chaotic and densely interconnected, with thousands of moving parts navigating around each other simultaneously. But computer systems cannot store information in chaos. They require absolute, rigid mathematical structure. When designing a database, resolving that real-world chaos into digital logic has very little to do with writing code. It comes down to defining the exact nature of how distinct entities interact. We call this mapping cardinality. It is the mathematical rule set that dictates exactly how one specific data table is permitted to link to another. Without strict mapping cardinality, a database quickly loses its grip on reality. Data corrupts, records duplicate uncontrollably, and the entire system inevitably fails. Establishing these rules is the ultimate test of a database's structural integrity. If we map these relationships incorrectly, the system cannot function. In fact, the entire history of database architecture is a history of engineers trying to master cardinality. The modern databases we rely on today did not start out perfectly flexible. Early data models were built with heavy physical restrictions, severely limiting how relationships could be drawn between records. To understand how modern databases operate, we have to test the core rules of cardinality against those historical architectures and watch exactly where they break down. By examining these past failures, we expose the unavoidable logic that governs every relational database running today. Any successful database must accommodate three specific types of mapping cardinalities. Look at this diagram outlining the first type, one-to-one cardinality. Here, a single occurrence in the first table links to exactly one occurrence in the second. In an ideal system, one citizen holds exactly one government ID, and that ID belongs to exactly one citizen. The second type is one-to-many cardinality. Notice how one occurrence in the first table links to multiple occurrences in the second. A single retail customer can easily generate multiple purchasing orders over time, while each order belongs solely to that one customer. Finally, we have many-to-many cardinality. As the diagram expands, multiple occurrences in the first table link directly to multiple occurrences in the second. Think of a university. Multiple students enroll in multiple courses simultaneously, and those individual courses contain multiple overlapping students. While one-to-one and one-to-many connections are straightforward to map, the many-to-many relationship presents a structural nightmare that routinely destroyed early data models. Let's apply these rules to the first major historical architecture, the hierarchical data model. This model operates strictly as a top-down tree, as shown here. It's one-to-many relationships. One parent entity can have multiple children, but a child entity can never have more than one parent. Watch what happens testing a many-to-many relationship here. We start with a vehicle parent, branching down to a four-wheeler subcategory, which branches to a specific car. If that car logically belongs to both parents simultaneously, the tree breaks. The system rejects the connection. You cannot accurately map a modern business if a child entity is strictly forbidden from reporting to multiple parent entities. Because reality relies heavily on many-to-many interactions, the hierarchical model's rigid top-down constraint quickly made it obsolete for complex systems. To solve that fatal flaw, engineers developed the network data model. Look at this structure. It completely removes the single parent rule. Any entity can now connect to any other entity in an open graph format. This successfully allows for many-to-many mapping cardinalities. But removing all constraints creates a new consequence. Without a standardized grid, tracking data inevitably generates a massive, tangled web of cross-connections. Querying, updating, or maintaining that web at an enterprise scale becomes dangerously inefficient. The system becomes too complex to safely modify. Solving cardinality restrictions by allowing infinite, unstructured connections simply traded a structural bottleneck for an unmaintainable maze. The modern standard that conquered both the bottleneck and the maze is the relational data model. In this model, the structure is standardized into grids. Entities become tables, attributes become columns, and occurrences become rows. This grid system handles one-to-one, one-to-many, and many-to-many relationships flawlessly, avoiding both rigid trees and tangled webs. The paradox of this system lies in how we manage data repetition. To maintain data integrity, developers are taught to ruthlessly eliminate redundancy. But to build relationships in a relational model, redundancy is mandatory. We resolve this through controlled redundancy. Because we can no longer draw arbitrary lines between nodes, we must deliberately duplicate specific pieces of data to form a link. Here is the exact mechanism. A primary key from one table must be intentionally copied into the second table. This duplicated column becomes a foreign key. It acts as the physical tether that makes relational cardinality possible. This deliberate, highly controlled repetition is the only mathematical way to link separate records without destroying the integrity of the grid structure. The relational model won out over older architectures by weaponizing controlled duplication to solve the cardinality problem permanently. Because relational tables require exact foreign key placements, building them blindly in code often leads to catastrophic architectural errors. To prevent this, engineers use the Entity Relationship, or ER, data model. This is not a programmable architecture, it is a pictorial blueprint. The ER model uses a specific visual grammar. Rectangles represent the core entities, or tables. Ovals represent attributes, columns containing traits like an ID number or name. Diamonds represent relationships, clarifying how entities connect, mapping a many-to-many link between students and courses. Mapping the entities, attributes, and relationships on paper first ensures the mathematical logic is sound before a single line of code is written. From the rigid trees of the hierarchical era to the modern relational grid, database design is a pursuit to capture the complexity of real life. ER diagrams and rules like controlled redundancy are simply the methods required to tame that complexity. In database engineering, the software is secondary. The underlying logic of the relationship must always dictate the structure.